Welcome back. Last lecture we discussed tandem queues using reversibility arguments, right. So, we considered, just to give you a recap, you considered a queue in which there is a Poisson lambda arrivals and a server of rate mu 1, and the customers that leave queue 1 immediately enter another queue with an exponential server of some rate mu 2, alright. So, this is the tandem system we studied. We know that the departure process, if you look at the departure process getting out of the first queue is independent of the present state of the first queue, right. This is something from Burke's theorem. So, what happens is that you can be these two queues at any given time t, they end up having independent states, right. So, if x t is the number of customers in this queue at time t and y t is the number of customers in this queue, then x t and y t turned out to be independent for any t, all right. And in steady state, we said that you will have probability, I mean, for a very large t, or either you start in steady state or wait for a very large amount of time. So, you will have probability x t equal to m, y t equal to n, which just products out into, so this of course is true for all t, x t equals m times probability y t equals n. So, this is of course always true for any t, and this is true in steady state. You will have the first one being mm1 and the second one being mm1. You have 1 minus rho 1 to the m, 1 minus rho 2 to the m, right. So, at any given time t, these two tandem queues behave as though there are independent mm1 queues. Of course, the queues are not independent, right. In fact, if you look at x t for some t and y tau for some other tau, they are not independent, they will not be independent in general, right. It is not at all the case that the process x t is independent of the process y t, that is not what we are saying. But the random variable x t for a fixed t is independent of the random variable y t for that t, right. That is what we are saying in this tandem queues. And we also argued that if you have FCFS, the time spent in the first queue and the time spent in the second queue by a customer are independent, so that the total time spent in the system can be added up as independent random variables, right, and that is because of part C of Burke's theorem. We argued all of this in the last lecture. Then we also had an example where some fraction of customers are sent back into the queue, right. That is a single, it's like a feedback system. In that case, what happened is that the arrival process into the queue was not Poisson, but the entire system could still be seen as an MM1 queue with a service rate mu times q, where q is the probability of leaving the system, right. So, these are things that we saw in the previous lecture. Now, this kind of networks where you have either tandem queues or some fraction of customers going back into one of the queues. You could have 3 or 4 queues where, you know, from Q3 you could go with some probability to the second queue, and the output of second queue could either leave the system or go back to the first queue. All sorts of these things are possible, okay. And these kind of with exponential service rates and Poisson arrivals. So, these kind of networks are known as Jackson networks, okay, and that is the topic of today's discussion. So, what is a Jackson network? It is just a generalization of tandem queues and these feedback queues, all right. So, you have some k nodes, okay. So, I am going to say the k nodes. What is a Jackson network? There are k nodes, each with an exponential server exp mu I equal to 1, 2 dot k. Okay. So, the ith server has a ith node has a server which serves with service times exponential mu I, alright. There is also a notional node 0 which is a notional exogenous node. So, node 0 is external to the system. It is better to not think of node 0 as one of the nodes in the system. You can think of it as something outside from which exogenous traffic comes into the Jackson network, and once service is completed, the traffic that leaves all these queues goes back into node 0. Okay, you can view it that way. Okay, so the picture is as follows. So, you have some, let us say that is node 1. Okay, so maybe this is, maybe I should draw squares so that this, so that you don't you know, you look at it as some CTMC or some such. So, there is a node 1, there is a node 2, let us say there is a node 3 and so on. Okay. So, what happens is there is traffic, there is some node 0 outside which you can view as exogenous node, alright. So, traffic comes to each of these nodes from the external node with some rate. Okay. So, let us call these rates exogenous arrival rates as R1, R2, R3 etc. Okay. So, there is traffic coming out of this exogenous node, okay, of some rate lambda naught. Okay. And you know, you can view it as, so these R1, R2, R3 they are all Poisson processes. Okay. So they are Poisson processes of rates R1, R2 and R3, they are independent Poisson processes. Now, since we are looking at a notional node 0 from which all the traffic is coming, you can split, you know, you can do a Bernoulli split with probability, you know, Q01, Q02, Q03 let us say, and you can say R1 is equal to lambda naught Q01, okay, and then that goes here, and likewise the split traffic of node 2 goes here, split traffic of node 3 goes here, alright. So, that is how the exogenous means arising from outside this network, right. So, this exogenous traffic comes in at these Poisson rates R1, R2, R3 which are simply lambda naught Q01, lambda naught Q02, lambda naught Q03, right, and there is exponential mu1 server here, there is exponential mu2 server here, exponential mu3 server here, alright. And upon completing service, let us say I am a customer who arrived first at node 1, upon completing service at node 1 with probability, let me draw it in a slightly different, you know, with probability Q12 I go to node 2 and probability Q13 I go to node 3 and probability Q11 I loop back to node 1. So, this is like looping back to the same node is like what we studied in the previous class, where some fraction of traffic just went right back into the same queue, right, and with some probability let us say Q10 it goes back, I mean Q10 it leaves the network, okay. So, I am going to say that it goes back to node 0 which is my both my origin and sink of all traffic, okay. This node 0 is just notional, okay, you can just think of it as leaving the network completely. Likewise, if I arrived from the exogenous node to this mu2 server, then I can go after completing service for exponential mu2 amount of time, I can go to Q2, this is Q21, I can go here with probability Q23, Q22 and so on, right. Likewise for, you know, likewise for node 3, I can do the same thing for node 3 or go back to node 0. So, this Q20 just goes back to node 0, Q30 node goes back to node 0, right, with some probability I go back to where I came from, alright, I just leave the network. So, this is how a Jackson network works, alright. So, this picture may look quite messy, but really the concept is very simple. You have exogenous traffic of different rates. If you do not want to think of this R1, R2, R3 as coming from the same process lambda naught and then split, that is perfectly okay. You can just think of R1, R2, R3 as being rates of independent Poisson processes coming at exogenously to these nodes, alright. After completing service with some probability Qij, I go from node I to node j, okay, and probability Qi0 I leave the network, okay, it is as simple as that. So, this picture may look unnecessarily complicated, but it is really not that complicated. And successive, so you have this whenever I am in node I, the successive choices of going to some other node j, this probability Qi is probability Qij, right, and these choices are independent across across successive service completions at node I, alright. We also assume that the routing is instantaneous, okay. So, there is when I leave node I and go to node j, the moment I depart node I am already have already entered node j, okay. These are all assumptions that we are going to make. So, this is called a Jackson network, okay. Now, if you look at this system, we want to find out how the system operates, alright. In fact, what we can see is that this system corresponds to a Markov chain, okay. So, we are going to put a state of the system, okay, at some any time t, okay. I am not going to make time t explicit. So, I am going to call it some vector, let us say m1 m2 dot 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 mk, which corresponds to the, so mi is the number of customers in node I, okay. So, this is my state of the system, okay, and we are going to argue that the state of the system m, which is simply the vector of the number of customers in each node, evolves according to a CTMC, okay. See, that is easy enough to see, because you have the exogenous arrivals are Poisson, and then you are splitting the departures in a IID fashion, right. Let me now say how the transition rates work, okay. Q, let us talk about Q m comma m prime, okay. These are transition rates. Transition rate from m to m prime. So, you have two different states m and m prime, which correspond to the number of customers in each queue, and what are the transition rates, okay. Now, as it what you can easily show is that if, so what are the three things that can happen? There are only three possibilities, right. So, let us say the system is in some state m, okay, m1 through mk, and so what is possible here, right. Remember that you cannot have simultaneous arrivals or departures. So, we are going to ignore that. So, they could be, the first thing that could happen is an arrival to some state, alright. So, if there is an arrival to an ith node, right, the ith entry mi alone will increase by 1, right, that is possibility number 1. The possibility number 2 is that some packet, some customer in some node j completes service and leaves the system, in which case mj, the jth entry will reduce by 1. The third possibility is that somebody completes service in some node j and goes to node I, right, in which case the state will go from, the jth entry will reduce by 1 and the ith entries will increase by 1, entry will increase by 1, okay. These are the only transitions that are possible, right. So, if you look at if you just define ei to be the vector of zeros except there is a 1 at the ith position, otherwise all zeros, then you can write down the transition rates as follows. You can write q m m prime as so let us look at the arrival first. Okay, let us say there is an arrival in an exogenous arrival to some node node j, all right. So, that will happen with rate lambda 0 q 0 j, which is simply your r j, right, with sorry, this is the rate of the transition whenever m prime is m plus e j, right. So, the jth, so you can go from m to m prime or m to m plus e j at this rate, or you can leave, right. You can have mu I at node I, you can have a service, so which happens at that rate for m prime is equal to m minus e I for, so this is true only for m I greater than 0. I mean, you can have a departure only if there is somebody, I mean there has to be a non-empty, the node I has to be non-empty for this to happen, right, whereas the first one can happen in any case. So, this is true for right, this is true for, it can happen in any of the k nodes, the arrival can happen in any of the k nodes. The second transition, which corresponds to an exogenous departure, happens when you have somebody in service, right, at least one person in service. And third possible transition is that you have a departure from one of the nodes immediately joining some other node, right, that is also possible. So, that happens with probability mu I q I j. So, I complete service in node I, but I do not leave the system, I instead go to some other node j, right. This happens at rate for this case, right, m minus e I leave node I, but I end up going to node j, right. This is for m I greater than 0 and for this is also for 1 less than or equal to I less than or equal to k. So, these are the possible transitions of the CTMC. So, what are we saying? The Jackson network described above, the state m, which is the vector of the number of customers at any given at some time, right, is evolves according to a CTMC whose transition rates are given like this, right. You go from a vector m, a state vector m, to a state vector m prime at these rates, and there are only 3 possible transitions that are possible. All other q m m primes are 0. Okay. So, maybe I should write that also. Maybe I should just erase this and say equal to 0 otherwise. No, there is no other state transition. Okay. These are the only possible transitions. Now, for this kind of a process, I want to determine, so these are the transition rates, right. So, what are the things that are of interest to me, all right. I want to determine the steady state behavior, right, that is the main goal of this exercise. I want to find out P of m, where m is some state vector. What is the probability that my state vector is m, right. Now, the issue is, I mean, is this system reversible? The answer is that the system is not reversible. So, even if you look at this very simple system, which this this tandem queues, I should have probably mentioned this in the previous lecture itself, even this tandem queue system is not really reversible. See, we are using, we are making heavy use of reversibility arguments and Burke's theorem for the first queue to infer something about the process in the second queue and concluding certain independence and MM1 property and all that. But If you look at the process XTYT in this, even in this tandem queue, the process XTYT considered as a vector, of course this is a very simple Jackson network, right? It is not a reversible CTMC at all. If you look at XTYT as a state vector, because you can have a transition that corresponds to a decrease in xt and an increase in yt whenever there is a customer going from one queue to the other, but the reverse transition is not possible, right? You do not have any customers going from yt to xt, right? So, the network is not reversible, all right. So, I mean it is pretty clear that the more general Jackson network that we have put down here, this messy network cannot be reversible, all right. So, the Jackson network running in forward time and the in reverse time will not look statistically identical at all, but we can still use some guesswork theorem to conclude what its steady state properties look like. So, the key issue is that although the Jackson network is not reversible, if you run the time in reverse, the hypothesis is that the time reverse system is another Jackson network. It is not reversible in the sense that it is statistically different from the network we have put down, but the reverse system will be a different Jackson network. And as it happens, we are able to guess the reverse transition rates of that reverse Jackson network. We hypothesize that the reverse network is a reverse Jackson network with a different set of rates. We are able to do some guesswork and guess those reverse transition rates, and from there we are able to infer some steady state probability using the guesswork theorem that we studied before. Okay.